Hello friends, in the last video we have discussed first few steps to design a controller using hardwired approach to solve Booth's multiplication. In today's video we'll discuss next few steps and we'll try to cover the complete hardwired approach to design a controller to perform Booth's multiplication. Let's start the video.
So this was the step number 6 we have seen in the last video. So I hope this diagram was clear for you, because this is very important to understand before we jump for the step number 7. And we know in the step number 6 we have identified total C0 to C9. There are total 10 different control signals I need to generate at the different times of at different clock cycles, so that I can get Booth's algorithm to be implemented, right? So we'll continue with the next step. Step number 7 is the block diagram of controller. Now we are ready to draw the block diagram, actual block diagram. This is how our control unit or controller will look like, the block diagram I'm talking about, where I will have a master clock as input. As I told you in the very first class also, that we have, not very first class, very first class of this one control unit, that will have 3 different types of inputs in our control units. What are those? One master clock, then one command signal, so this reset is nothing but the command signal, and the status information. So status information I will get from these 3 different lines in this Booth's algorithm. So what are those? Q1, Q0, whether I have to go for addition, subtraction, and this Z will tell me whether I have to stop my algorithms or not. If Z equals to 1, I will stop. If Z equals to 0, I will continue. Why? From this we got the value of Z. If it is 1, means L equals to 0, means count equals to 0, I have to stop. And output I will get 10 different control signals. So I hope this step is also not a very difficult step. We'll go for step number 8. So step number 8 is to draw a state diagram. Now we have the algorithm, we have all the set of control signals, we know all the steps, right? We have to make some states now, that at 1 clock pulse what we'll do. How many steps I can perform in 1 clock cycle. Based on that I'll make some states. So how to make those states? So T0 is the first step of the algorithm, where I can initialize all these things like A equals to 0, L equals to 4, and M equals to inverse. So I don't need 3 clock pulse to get all these things, right? These are very simple tasks. So in 1 clock pulse only I'll finish these 3. A equals to 0, L equals to 4, M equals to inverse. What is M? Multiplier. And in second clock pulse T1, what I will do? I will take Q as input. Q is multiplicator. Now you will tell, you may ask me, sir, if I can take A, L, M in first clock pulse, why not Q in the first clock pulse? Why I need one more clock pulse for that? Why I need one more state for that? The answer is very simple. This Q is not only Q here, right? If you take only Q equals to inverse, you can do it in T0. But what I am doing here, Q I have 2 different parts, right? The first bit of Q is actually working as Q minus 1, right? So in Q also I have a partition. First 4 bit is for multiplicand and the last bit is for Q minus 1. So because of that I have one more state. Other than that, if you have only Q equals to inverse, you can use in T0 also. Fine. So T0, T1 is done. In T2 I will not do anything, but from here I will decide which way I have to go based on the values I got from the previous step, right? So if I am getting 0, 1, I will go to next step, step number T3 this side. If I get 1, 0, I will go to the next step this side, T4. If I get 0, 0 or 1, 1, I will go straight to T5. What is T5? T5 is nothing but shifting operation, right? So shifting is important or must for all the cases, right? Whether you go left, right or straight, you have to do the shifting. Fine. Now from T2 I can have 3 different ways, right? This is one way, this is another way, this is third way. By default I am taking this way. This is the default way I am taking. Say this is the way I am taking. And if I take this is a default way, then I will have 2 other options, right? You can take this also. If you take this as a default way, then you will have 2 other options. If you take this as a default way, then you will have 2 other options. So any way you can take as a default way. So I am taking this one as a default way. Fine. So in T3 I will do A plus M, A minus M, and T5 I will do shifting. And if Z is equals to 1, so I will go to T6. What is Z equals to 1? Z equals to 1 means your count equals to 0 means you have to stop it. Then I'll go to T6. Otherwise, if it is not 1, I'll come back to T2 again. If it is 0, Z equals to 0 means count is not 0. So I'll come here T2 and I'll follow the same steps again and again until and unless I get count equals to 0 or Z is equals to 1. So once everything is done, then I'll come back to T6. In T6, I'll send this A to my user. In T7, I'll send Q1 to 4, not everything because Q0 is Q minus 1, right? To the user. Then the last state is the halt state, which we have already seen in the last video. So your result will be keep looping here in this state T8. It will be there in T8 until and unless you reset the controller. It will be there only. It will be keep looping, self looping. So I hope step 8 is also not so difficult, right? Now step 9. So we have seen the trial processing section in detail about those trial processing section, how to generate control signals, everything we have seen for the trial processing section, right? So actually to implement the Booth's algorithm, we need 2 more important hardwares along with all those resistors and other subtractors. What are those? One is mod 16 counter. Why mod 16 counter? Mod 16 counter will help you to count the timing. You know counter, right? So mod 16 counter means it will get some 4 inputs. Any input it may be 1 1 1 1 1 0 1 0, whatever 4 inputs it can take. So irrespective of any input, your counter will start from 0 0 0 0 and it will go up to 1 1 1 1. Means 0 to 15. Means 16 clock pulses. Fine. So it's not that it will stop at 1 1 1 1. Once it reached 1 1 1 1, it will again come back to 0 0 0 0 0 0 0 1 like this. It will be continuously going on. It will count. That's why we say it's as a counter. It can count from 0 to 15. Irrespective of any input. It will never depend on the input that if this is the input then counter will be this. No. Counter is counter. It will keep going on. 0 0 0 0 0 0 0 1. It will keep going on. Fine. So next we need one 4 to 16 decoder. Counter is fine. Decoder. Why we need decoder? Because how many control signals I have? Total 10 control signals, C0 to C9 for Booth's algorithm, right? So I cannot send all these 10 signals at a time. I have to send one by one, right? So for that I will use a decoder. Which decoder you will use? Because I have 10 output signals, I can use 4 to 16 decoder. Obviously some of the output lines will be unused. I need only 10 output lines. Rest 6 output lines will be unused, but it's okay. I can use 4 to 16 decoder. And then a sequence controller. Sequence controller is a hardware only. This hardware tells you the sequence of the instructions. That if this is the instruction you are executing, what is the next instruction you have to execute? Fine, we'll see this in the next diagram. We have this. You will understand how sequence controller works. So these are the 3 major hardwares. Additional major hardwares I need apart from all the GPRs and adder subtractors. Now step 10 will have the final logic diagram of Booth's multiplier controller using hardwired approach. So this diagram looks like very problematic, very difficult. I'll try to make it very simple. Please pay attention and whatever I'm saying, please follow it. You can make a note also. Forget about everything. So from the previous slide, we have seen we need one 4 to 16 decoder. So first you draw this 4 to 16 decoder. 4 to 16 decoder means there will be 4 input lines and 16 output lines. Fine. So output lines, sorry, in the previous slide I said I'll deal with control signals here. No, I'll deal with states here. Actually, how many states we have? T0 to T9. So what I'm doing here, how many output signals I need, how many output lines I need? T0 to TA, total 9 output lines I need. Rest all will be unused. So I have 4 to 16 decoder, 4 input lines I have drawn and 16 output lines I have drawn, but I know I have only 9 states. So T0 to T8 will be used, rest will be unused. I think this much is clear for you. Fine. So next what I have, check it. So here in T0 or in the first clock cycle, when I start my algorithm, I am doing multiple tasks, right? A equals to 0, L is equals to 4, M is equal to in bus. For all these, I have 3 control signals to be activated. C0, C1, C2. C0 is equals to A equals to 0, C1 is 4, M is equals to in bus, C2 is 4, L is equals to 4. So in first clock pulse, I will enable 3 control signals. Means in T naught, this is nothing but T naught equals to C naught, comma C1, comma C2. So same thing I am doing here. In T naught, I have C naught, comma C1, comma C2. T naught is done. Check for T1. Sorry. In T1, what I am doing? Only one control signal I am activating, which is C3, right? So C3. So in T1, I will have only C3. I hope this is clear for you. Similarly, T2, I am not having any control signals. So in T2, I don't have any control signal here. So it's empty. Next, go for T4. In T4, what I am doing? In T3, sorry. In T3, what I am doing? C4 and C5. So go to T3. T3, I have C4 and C5. If you see, I have a OR gate here. Why I am using OR here? Because at the same time, I cannot have addition and subtraction together. That's why OR. Either it will be performing addition or subtraction. Either it will be T3 or T4. Fine. So either I can perform T3 or T4. I cannot perform both together, right? I cannot. So similarly at T5, I have C6, C7. So at T5, so this is 4, this is 5, I have C6, C7. And then I have C8 at T6, C9 at T7. So C8 in T6 and C7 I have C9. Sorry, T8 I have C9. So I hope you understood. In all the states, I have all these signals and I have added there. So I hope this 4 to 16 decoder and these states, these control signals are clear for you. You understood this, right? Next, we will see the next part of this block diagram. So this part is clear for you. Now I will come back to the left hand side. Right hand side is clear. I will come back to this looping and all. I will come back. So see here what we have. So here I know this is 4 to 16 decoder, means I need 4 input signals for this. These 4 input signals will be generated by this mode 16 counter. Means this is 0 0 0 0, next 0 0 0 1. Like this it will go up to 1 1 1 1. These are the clock pulse. So in the first clock pulse, you activate one of this signal, T naught. 0 0 0 0 means T naught. These 3 will be done. Next, in the next clock pulse 0 0 0 1, T1 means C3 will be activated. Like this it will work. So this output is clear for mode 16. Now mode 16 is connected with some master clock, some enabled. So obviously it will be 1. If it is 1, then only it will work. If it is 0, it won't work. Then reset button is there. If you want to reset it, you have to press it or you have to make it 1. Then there is a L line. So initially you have to put it 1 so that you can load some data. If it is 0, then you are not taking any input to the mode 16 counter. So I have mode 16 counter is clear for you. This is not so difficult, right? Now mode 16 counter also will take some inputs, as I told you. It may be any input. Irrespective of these inputs, the clock cycle will be going on sequentially. I know that. I told you. So these are the input lines to the clock or the mode 16 counter. So what are those? The input lines to the mode 16 counter is nothing but the output of your sequence controller. What is sequence controller? It will control the sequence of the instructions or sequence of the states. What is the next step you have to execute? Fine. So by default, it will go sequentially, right? First T0, then T1, then T2, then T3, because this is mode 6. This is it's 64 to 16 decoder, so it will go one by one. But sometimes I have some looping also. I cannot go sequentially, right? Somewhere by seeing the condition as Q0, Q minus 1, I have to take left, right, straight. So I have to decide like this. So who will tell me those things? Sequence controller. Sequence controller will give you the state number, which state you have to follow. Fine. Now how it will follow this state? How it will give you? For the sequence or sequence, for the sequence execution there is no problem. But if there is a looping, there is a problem, right? So this sequence controller will tell your mode 16 counter about the looping, that there is a looping, please go to that particular stage. You understood that? So for that, your sequence controller should know about the looping conditions. Where are the loopings? From where I'll know? I'll know from this state diagram. Where the looping? See here, this is the default way I took, right? So there is a looping. T2, T3, T5, I have a loop. T2, T3, T5. There is a loop. Now you can take this way also. Since I have taken this is the default way, so I have a looping here. T2, T3, T5. And also in T8 we have a self-looping condition. So these are the 4 states where I have some problems or I have some looping. Other than that, you can go sequentially. So T2, T3, T5 and T8 I have some looping. So I will get back some inputs from here to my sequence controller. See, T2, then T3, then T5 and T8. 2, 3, 5, 8. 2, 3, 5, 8. So wherever there are some looping, I am taking this back to my sequence controller, this 4. Fine. Apart from that, what else I need? I need the value of Q1 and Q0 to decide where to go, whether it's 0, 0, 1, 0 or 1, 1. Then I need the status of Z also. If it is 1 means count is 0, I will ask my mode 16 counter or my controller to stop the algorithm. Fine. So I have this 3 plus 4, this 7 inputs to sequence controller is clear for you now. This mod 16 counter is clear for you now. 4 to 16 decoder is clear for you now. And how these signals are arranging irrespective of all these states, I think it's clear for you now. Fine. So next step will go, it will make you more clear for you. It will be more clear for you to understand now how it works. So next one is the truth table for this sequence controller designing, sequence controller, how it works. We'll see in detail. So I think this image is blurry, so I'll make it a smaller so that it will be less blurry. So what I'll do is I'll make it a smaller one. And for your understanding, I'll copy this state diagram also to that place so that it will be easy for you to understand how it works. So what I'll do is now I'll start this. See, in my sequence controller, what we have seen, what are the inputs? There are 7 inputs: Z, Q1, Q0, then T3, T2, T3, T5 and T8. So Z, Q1, Q0, T2, T3, T5 and T8. And then now in output lines, what are the outputs I have? L, D3, D2, D1, D0. So L, D3, D2, D1, D0. Now we'll see the truth table. So L is 1 everywhere because I'm loading every time, so nothing to do with L. We'll see this side. What we have? Say Q1, Q0. What are the different possibilities I have for Q1, Q0? I can have 1, 0. I can have 0, 0. I can have 1, 1. I can have 0, 1 also. But this is the default path I have taken, I told you. So by default, I will go there. So if I skip this, I have 3 different other options. Either I can have 1, 0, 1, 1 or 0, 0. So Q1, Q0, I can have 3 options. 0, 0, 1, 1 or 1, 0. 0, 0, 1, 1 or 1, 0. This is the default path I am skipping. Fine. Now, suppose the Q1, Q0 is 0, 0 and I am at T2. I am at T2 and Q1, Q0 is 0, 0. This 1 means I am at T2. Fine. And the value of Q1, Q0 is 0, 0. If so, then where I will go? If I am here and I am getting 0, 0, I'll go straightly to T5. Right. So the output is 0, 1, 0, 1, which is 5. T5. Means if you are at T2 and you are getting Q1, Q0 as 0, 0, then go to state number 5. 0, 1, 0, 1 is 5, right? You convert it to decimal, you will get 5. Fine. If it is 1, 1, I am at T2, I am getting 1, 1, then also I will go to T5 only, so 0, 1, 0, 1 only. If it is 1, 0, I am at T2 and I am getting 1, 0, where I will go? State number 4. So I will go to 0, 1, 0, 0, which is 4. If I am at T2 and I am getting 1, 0, I will go to state number 4. Fine. Next what? T2 is done. Next T3. So if I am at T3, where I will go? I don't have any other option. I will directly go to T5. So if I am at T3, where I will go? T5. 0, 1, 0, 1. I don't have any other option, right? You are at T3 and you have to go to T5 only. Fine. Next we have T5. If you are at T5, now it depends on the Z value, right? If you are at T5 and Z equals to 0, then where you will go? You will go back to T2. If Z equals to 0, you are at T5, you will go to step number 2. So 0, 0, 1, 0. Otherwise, it's straightforward, you will go like that. And finally, we have T8. If you are at T8, so where you will go? You will be there in T8 only. 1, 0, 0, 0 is 8. You understood the truth table of sequence controller, I guess? Fine. So next is PLA design. What is PLA? You will get in detail in your digital system digital system codes. PLS is programmable logical array. So it's a hardware. So unlike your sequential hardware where you get a fixed type of hardware, say I am asking you to buy one adder or subtractor, whatever hardware you will bring, it will perform the specific task only. You cannot modify it. But PLA is such type of hardware where you can modify as per your necessary. So you will get in detail in digital system. So how it looks like? For all the inputs, I will have one input line as well as one not input line also. So Z, Q0, Q1, T2, T2, T3, T5 and T8. So everywhere I have the single input line and I have one not input line also. So the best, forget about this part now. The basic idea is whenever you need Z, you just on this switch, will have some fuses actually. On this switch, it will work. If you need Z0, you will on this signal or you put some cross symbol here. So Z0 will work. Fine. So everywhere we have the cross connection. So wherever it is necessary, cross it. If not necessary, don't cross it. That's it. Now see the inputs, what we have. For the first row, what I have? I'm sorry. For the first input, I have 0, 0, 1. Alright, this side up to T8. 0, 0, 1 and rest nothing is there. So what I'll go? 0, 0, 1. Where is 0? Q1. So Q1 is 0 here. See, this not means 0. This is 1, this is 0. Q1 is 0. What is Q0? 0. What is my T2? T2 is 1. Rest all, nothing is there. So for the first row, this is done. 0, 0, 1. For the second row, 1, 1, 1. So this is 1, this is 1, this is also 1. Fine. Next one is 1, 0, 1. 1, 0, 1. 0 means dot. Fine. Next, what do we have? We don't have anything here. So we don't have anything here. Lastly, we have here 0 and T5 1. So Z equals to 0 and T5 is equals to 1. Nothing else. So this side I think it's clear. Wherever I have some values, I am putting either 1 or 0. I am putting some cross for all these variables, right? Now come to this side. What are the outputs I have? L, D3, D2, D1 and 0. So L, D3, D2, D1 and 0. So all these input lines from all this Z to T8, I have some AND gate and the output of AND gates are again connected in a crossbar way with the OR gates like this. So what is the first output you are getting here? All ones. So in L, I will put everywhere cross. All ones. If necessary, if 1 then put cross, if 0, no cross. Fine. So 1, 1, 1, 1, everywhere 1. So for D3, what is the output? Only one place I have 1, which is the last one. So in D3, only at the last place, you just cross it. Rest all are zeros. For D2, 1, 1, 1, 1, 0, 0. 1, 1, 1, 1, 0, 0. Fine. Then for D0, D1, what do we have? For D1, we have 0, 0, 0, 0, 1. 0, 0, 0, 0, 1. Then 1, 1, 0, 1, 0, 0. 1, 1, 0, 1, 0, 0. Now if I ask you to write down the equations, if I ask you what will be P0, can you tell me? Yes, P0 is nothing but Q1 bar dot Q0 bar dot T2. Then P1 is what? Q1 dot Q0 dot T2. What is P2? P2 is equals to Q1 dot Q0 bar dot T2. From here you can easily find out the equations, right? And this side also, if I ask you what is L, L is P0 plus P1 plus P2, P3, P4 and P5. What is D2? D2 is nothing but P5. What is D? Sorry, this is D0. What is D0? P5. What is D2? D2 is nothing but, sorry, this is D3, this is D2. What is D2? D2 is P0 plus P1 plus P2 plus P3, right? So like this you can draw all the equations. So next is the equations only. P0 is equals to Q1 bar dot Q0 bar dot T2. So Q1 bar dot Q0 bar dot T2, because this is the AND gate. And here I am using OR gate, so everywhere it will be plus. Suppose I want D2. D2 is what? P0 plus P1 plus P2 plus P3. Let's see. For D2, P0 plus P1 plus P2 plus P3. So like this you can have all the equations. And this side we already have. In T0 I have C0, C1, C2. In T1 I have C3. So you have already seen. So that's it about the hardwired approach to design a control unit. And we have seen a specific task to perform, which was Booch algorithm. So for Booth's algorithm, we have seen how to design a control unit using hardwired approach. So in my next video, we'll see how to design a control unit using microprogrammed approaches. So thanks for watching my video. Thank you.